Gait recognition, identifying individuals by how they walk, is a powerful biometric technique that operates non-invasively, making it ideal for surveillance and security. Unlike facial recognition or fingerprinting, gait can be captured remotely without cooperation, even from low-resolution or distant views. But how do we represent walking patterns in a way that machines can understand? At the core of modern gait recognition lies the binary silhouette, a simplified black-and-white image of a person's body contour, extracted through segmentation. These silhouettes are typically 64 times 44 pixels, forming a sparse binary sequence across time. While they strip away distracting details like clothing or carried objects, they preserve the essential motion cues of walking. Now here's the key insight. Binary silhouettes aren't just visual data, they're discrete, sparse, and structured, much like natural language. This structural similarity opens a fascinating possibility. What if we could treat gait silhouettes not as images, but as words in a language? Recent approaches have relied on vision backbones, CNNs, and transformers to extract continuous features from these silhouettes. But continuous encodings inevitably smooth out the inherent sparsity of binary data. The result? Subtle motion cues, tiny shifts in body posture, foot placement, or limb velocity are lost in the noise. Enter large language models, systems trained on massive amounts of text, capable of modeling long-range dependencies, capturing fine-grained semantic variations, and understanding context. They operate on discrete tokens, each represented as a one-hot vector. And guess what? So do binary silhouettes. That's where the idea of silhouette language encoding comes in. We ask, can we translate binary gait silhouettes into a language-like token space, so that LLMs can interpret them as sequences of words that describe walking patterns? The answer is yes, but not without challenges. First, token density. A single 64 times 44 silhouette contains 2,816 pixels. If each pixel were a token, you'd end up with over 20,000 tokens per frame, far beyond the capacity of any practical LLM. That's like trying to feed a 10,000-word sentence into a model, designed for 32,000 tokens total. Second, token frequency distribution. In natural language, a few high-frequency words like the and dominate, while most words appear rarely. But in raw silhouettes, nearly every pixel is active, leading to a dense, uniform distribution that doesn't match the skewed, long-tail distribution of real language. To bridge this gap, we propose the Contour-Velocity Tokenizer, a novel module that restructures the binary silhouette into a meaningful, language-compatible format. Here is how it works. Step 1. Extract the contour. Instead of treating every pixel as a token, we isolate the boundary of the body. By zeroing out all interior pixels and preserving only the outer edges, we drastically reduce token density, compressing it from 21% to just 4.5%. This is no longer a noisy blob, it's a clean, skeletal outline. Step 2. Capture motion with velocity maps. We compute the difference between consecutive contour frames, generating a velocity map that encodes how the body moves over time. This map is even sparser. Only 1.8% of pixels are active, making it ideal for language modeling. More importantly, it captures subtle gait dynamics. A slight sway, a heel strike, a shift in balance, all encoded as low-frequency tokens. Step 3. Expand and align. The contour and velocity tokens are then passed through a learnable multi-layer perceptron that expands them into the full text token space. Crucially, we apply a learnable frequency weighting, scaling each token by the inverse of its observed frequency. This balances the distribution, pushing low-frequency motion patterns, which carry rich discriminative information, into a position where the LLM can actually learn from them. The result? An implicit silhouette vocabulary, a shared discrete space where gait patterns become interpretable as sequences of meaningful, language-like tokens. With this framework, we build Silhouette Language Model, a dual-branch architecture. The visual branch remains a standard gait backbone, like Deep Gait V2P3D or GL Gait, extracting continuous features from the original silhouettes. Meanwhile, the Silhouette Language branch takes the CBT-encoded tokens and feeds them into a pre-trained LLM, such as QN3 embedding. Because the LLM is frozen, we avoid overfitting and preserve its rich, pre-learned knowledge. The language model learns to interpret the silhouette tokens, not as pixels, but as motion events. Ankle flexion, waist extension, balance stride, plantar flexion, and so on. Finally, a lightweight adapter module aligns the text embeddings from the LLM with the visual features from the backbone, fusing them into a unified representation for recognition. Now, why does this work so well? Let's look at the evidence. On Gait 3D, SilLang P3D achieves 76.9% rank 1 accuracy, a plus 2.5% improvement over the baseline. On GREW, it hits 80.6%, a plus 2.9% gain. And on SUSTech1K, where variations in clothing, carrying, and occlusion are extreme, SilLang improves overall rank 1 accuracy by plus 1.9%, demonstrating superior robustness. But the real power lies in generalization. When paired with GL Gait, SilLang GL achieves 78.4% rank 1 on Gait 3D and 81.2% on GREW, outperforming even the latest state-of-the-art models, including Gait LLM and CLTD. And it's not just better, it's more efficient. The language branch adds minimal overhead, and since it's frozen, training is stable and fast. Ablation studies confirm the importance of each component. Removing the velocity extractor drops performance by 1.5%. Without the expand end-align module, the model fails to match text token statistics, highlighting the need for frequency alignment. And when we freeze the LLM while training only the visual backbone, we get the best results, proving that the language branch acts as a feature enhancer, not a learner. We also explored larger LLMs. Using QN3 embedding 4B instead of 0.6B boosted performance slightly, showing that higher dimensional embeddings reduce information loss during compression. Visualization confirms the theory. The embedding distributions of silhouette tokens closely mirror those of natural language tokens. And when we measure the distance between positive and negative samples, SilLang significantly increases the gap, improving class separability. This isn't just a technical trick. It reveals a deeper truth. Sparse visual data and natural language share a common encoding logic. Both are discrete, structured, and governed by statistical regularities. Just as vision models can understand text, as shown by DeepSeek OCR, language models can now understand Gait. This symmetry suggests a broader paradigm, a unified framework for discrete representations across modalities. From DNA sequences to protein structures, from handwritten digits to gait patterns, LLMs can embed them all. In conclusion, SilLang redefines how we think about gait recognition. By translating binary silhouettes into a language-like token space, we unlock the full potential of LLMs, not just for text, but for motion. We bridge visual sparsity and linguistic discreteness, enabling machines to see walking patterns not as images, but as stories. And in doing so, we take a bold step toward a future where language models don't just understand words, they understand how people move.